Okay, so the next section is on non-planar graphs. So we discussed planar graphs in the previous couple of lectures. We characterized planar graphs. We established the necessary and sufficient conditions for a graph to be planar. So now, dealing with non-planar graphs, we know now that these are graphs that you cannot draw without having at least one crossing. So now the question becomes, if I have a non-planar graph, what is the smallest amount of crossings that occur within a drawing of this particular graph? So taking that graph and looking at all its possible configurations, drawing it in all possible ways. If I look at the drawing of that graph with the smallest amount of crossings, then that is known as the crossing number of a graph. So it's amongst all the drawings of the graph. It's if you count all the crossings of each one of the drawings, you look at the smallest value amongst all of those values, and that is the crossing number of a graph. So remember, some non-planar graphs are close to being planar. In other words, it's just a question of removing one or two edges and the graph is planar. In the sense that they can be drawn with a few edges crossing. So the definition of the crossing number, again, is as I explained, is the minimum number of crossings of edges over all the drawings of G in the plane. And it's denoted by this parameter here. So CR of G counts the smallest number of crossings. So now if a graph is planar, obviously that means the crossing number is going to be 0, because amongst all the drawings of the graph G, you're going to find a graph with 0 crossings. Okay, so CR measures that value. As an example, how would we go about improving that a crossing number of a particular graph is an exact number? As an example, if you look at K5, to prove that the crossing number of K5 is 1, you need to show that the crossing number of K5 is at most 1, and it's also at least 1. It's at least 1 because it cannot be 0, because K5 is a non-planar graph. It's at most 1 because I can demonstrate a drawing of K5 which has got only one crossing, and the drawing there is that drawing there. There's the crossing we're talking about. So it involves finding two inequalities, an upper bound and a lower bound, the upper bound being the same as the lower bound. Right, so we can actually find a lower bound for the crossing number, a relatively elementary lower bound, using planar graph. The result we found for a planar graph, the bound that we derived for planar graphs on the number of edges. Now, just an observation, we can draw any graph such that no more than two edges cross in any point. So now what we're going to do is, when we draw a graph with crossings, we're going to convert that graph into a planar graph. And how would one do that? Is you would essentially place a vertex at each crossing, and you would construct a new graph, which is going to be a planar graph. So this brings us to the following theorem. So if G is a graph of order n and size m, where n is at least 3, then the crossing number of this graph is at least m minus 3n plus 6. So if you let C be the crossing number, then what we do is we convert this particular graph into a new graph by doing the following. You draw it such that it's got C crossings, and then what we do is we construct a planar graph, h from g, by simply adding a new vertex at each crossing. Okay, so as an example here, the K5, we take a vertex and we place it at that particular crossing, and the resulting graph is then definitely going to be a planar graph, right? Right, so so by adding the new vertex at each crossing, that essentially subdivides both crossing edges. So now the question is, this new graph, how many extra vertices does it have? Well, you placed a vertex at each crossing, and there are C crossings. So you're basically increasing the order of the graph by C, and the number of edges for each crossing. You are increasing the size of the graph by two times that particular crossing. So essentially, you're creating for each crossing, you're creating two edges. Right, so now you've introduced C vertices in your new graph. You've introduced two C edges. And therefore, this is a planar graph, right? So we know the size of this planar graph. The size of this planar graph is at most 3 times n plus c minus 6. And therefore, you can solve for the inequality and obtain that c needs to be at least m minus 3n plus 6. Okay, so that's an elementary lower bound for the crossing number. All right. So next up is the crossing number for graphs in general. There's not much known about the crossing number. However, they've investigated the crossing number for some special classes of graphs. And one of the classes includes all the complete graphs. So what exactly is the crossing number for the complete graph? Now, this number, they don't know the exact number. However, they have managed to find some lower and upper bounds. Now, we can derive very quickly an elementary lower bound by just using the previous result and doing the substitution for the size of the graph, right? Now, it turns out that you can actually improve this this lower bound considerably, and that brings us to the following theorem. We can actually derive that the crossing number is at least a fifth of n combination 4, okay, which is way better than the previous result. Right, so we prove use induction on n. The result is obviously true if n is equal to 5. When n is equal to 5, then the crossing number of K5 is obviously 1, and so the theorem holds for n equals 5. So we may assume now that the theorem holds for every value, integer value, positive integer value less than n, and then we prove that the result holds for the value n. Okay, so our induction assumption is that for k equals n minus 1, the lower bound holds. Okay, so let's take K5 and look at the crossing number of, let's take Kn, and look at the crossing number of Kn. And now what we're going to do is we're going to use a clever counting argument. So we're going to delete a vertex from Kn and then apply the induction assumption to this particular graph. And then we're gonna do it for every vertex every vertex of the Kn. We're going to form a graph G subscript I, which is Kn with the ith vertex deleted. Right, now deleting the ith vertex and forming the graph G subscript I, what you then do is you sum over all the crossings of the GIs. So you sum over the crossing number of GI for all I, and you denote this sum A. You denote this whole sum as A. Okay. Now we can bound A in two different ways. Okay. You can find a lower bound for A because you're adding over n graphs. Each graph has a lower bound according to the induction assumption of that. So you're adding how many crossings are you adding in total? You're adding at least n times a fifth of that inductive lower bound. Then the second way you can express a crossing of two edges A, B, and C, D in G appears in the ith drawing only if the ith the vertex that you deleted to get G subscript I is obviously not in that group of vertices. So hence A is exactly equal to n minus 4 times the crossing number of Kn. So why is that the case? Right, so just if we look at this representation here, so this right, so this is the whole graph. That's the whole graph Kn, right? Now if we look at a particular crossing in Kn, look at that crossing there. So now remember how we defined GI, right? GI is pretty much it's Kn minus Vi, right? Okay. Now, how many of the GIs are going to have this particular red crossing? Right, now that crossing exists in GI only when Vi lies doesn't lie in the vertex set containing these four vertices, right? So now go and count all the GIs that are going to have that particular crossing. How many are there going to be? There are going to be a total of n minus 4. So n minus of all the GIs, n minus 4 of them are going to have this crossing. Okay. So now what you do, that is for that particular indicated red crossing. Right now you do that for all the crossings in GI. You do it for all the crossings in G. So how many are there going to be in total? How many crossings are there going to be in G? Remember, there are so many crossings in G. CR of Kn, okay? So that is going to count the total number of crossings over all the GIs. Okay. Right, so going back then, combining the two inequalities, we get this inequality, and then you can go and solve for the crossing number, and that basically reduces to the desired result. Right, so for many graphs, as I said previously, for many graphs, their crossing number is actually not known. We provide a few examples. In actual fact, the crossing number for Kn is known exactly. And they've actually conjectured that it's equal to exactly that number, and they've managed to only prove it for n at most 12. So that's quite an interesting result. Right, now it would be appropriate to just look at a few more classes. We look at these powers of paths, the crossing number. Now we said the distance, remember, between vertices u, v of G is the length of the shortest path between the two, right? Now, if G is a graph and K is a positive integer, was natural number, then its kth power of g, denoted by that, is simply the graph that you obtained with vertex set of g, and where two edges u and v are adjacent, if the distance between them is at most k in g. Right, so g2 is called the square of g, and g3 the cube of g. So if you look at just an example, if you look at the square of g, where g is given as this graph here, right, so what you will do is you will join vertices that are at distance at most 2 from one another. Right, so for this vertex, you'll, as an example, join it to that vertex. You'll join those two vertices there. There you will join. You will also join that. Okay. Then these vertices, you will join them there. You'll join them there, and you'll join them there, okay, because they're all at distance at most 2 from one another. And again, these vertices, you'll join there, you'll join them there, you'll join them there, you'll join that there, and again, you'll join those vertices there, join them there, join them there, and again you will join that vertex there, 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 there. I think I've added all the necessary edges. Okay, so I mean that's how it works. So you just join the vertices, you take G and you just add extra edges. You join the vertices that are distance at most 2 from one another. So that's the square of G in that particular case. Right, so as an interesting class of graphs, what's the crossing number of powers of a path? So the crossing number of Pn is obviously 0, and the crossing number of P's squared is also 0 because both are planar, and you can actually just introduce the drawing of P squared, and you can draw it in such a way that none of the edges cross. Okay, so if we are to extend this to P3, to the cube of P3, then also P cubed is planar as well. Right, so why is P cubed planar? Because if we look at P3, P cubed, it means that we are joining the vertices at distance at most 3. Okay, so you have to join the vertices at distance 2 and at distance 3. So you're basically going to add these edges pretty much, right? So for that vertex, then you're going to join that to that vertex there. You're going to join it there. Right, this one you're going to join there. 1, 2, 3, and okay. All right, so there we've added all the possible edges, and that's still a planar graph, right? So P cubed is definitely planar as well, so it has a 0 crossing number. Right, so now the question is, what about P to the power of 4? Right, so what's the crossing number of P to the power of 4? Now, it's important to note that the size of P4 is 4n minus 10. We'll just quickly see why that is the case in just a moment. And that will imply, by our earlier theorem, what we do is we apply the lower bound that we obtained for the crossing number, which is that lower bound. Remember, we derived it, and then obviously it's 4n minus 10 plus 3n, 4n minus 10, minus 3n plus 6. Right, and that is obviously n minus 4. Okay, so the crossing number for p to the power of 4 is at least n minus 4. To prove that it's equal to n minus 4, we need to provide a drawing of Pn4 such that there are at most, well, there are n minus 4 crossings. Now, if you look at this quick example, this is what the drawing of p to the power of 4 is going to look like. Right. So here, this is that's a representation of p pn cubed. Remember now, we're not considering the actual. We considering it only for n equals 9, but the drawing of to extend the drawing to any n is going to pretty much look the same. So that is a representation for pn cubed, and this is a representation for Pn4 to the power of 4. And how many crossings are there in this case? Right, so there are n minus 4 clearly crossings. Now, if you were to extend this to n in general, your drawing is still going to look, it's still going to have the same, it's still going to look exactly the same, right? So you're always going to have this pattern emerging, which is going to count the exact number of crossings there. So we have equality in that particular case. So quickly to check why what the size of Pn4 is, that's a very straightforward counting argument. Again, just apply the definition. So we're going to, so we start off with n minus 1 edges, and then we go and add to that. So we're going to join that vertex there. We're going to join it there, 1, 2, 3, 4, and we're going to join it there. So for that particular vertex, we added 3 edges. For this vertex here, we're going to add that edge. We're going to add that edge there, and we're going to add that edge there. So that's distance 1, distance 2, distance 3, and distance 4, okay? And we're going to follow this process through for each vertex until we get to this vertex here, which we then, right, so I mean this path carries on there. So in that case, we're gonna add that edge there, add that edge there, and again, so we're adding 3 edges there. So in total, we've how many edges? Okay, so we've added for each vertex. We've pretty much taken. If we go and count the red edges we have so far, that's going to be 3 times n minus 4. Okay, and then what we're going to do is for that vertex there, we're going to add an edge there, 1, 2, and then for that vertex we're going to add another edge. Okay, so in total there we're going to add 3 edges. Okay, and then the edges on the path, which is n minus 1. Okay, and that is then going to be 4n minus 12 plus 2, which is minus 10. Okay, so it's not, that is the size of Pn to the power of 4. Okay, so now let's look at another example. Remember the graph KABC is the tripartite graph. It's the tripartite graph where we've got 3 vertex sets, A, B, and of coordinality A, B, and C respectively, and we in the partite set we don't add edges, we only add edges between the partite sets. Right, so, but in the case of K, we add all the possible edges between the partite sets. Right, so that is what the K stands for. So as an example, K322 is just 3 partite sets, 2 vertices in 2 of them, and 3 vertices in 1 of them, and we join all the edges between the partite sets. We don't add edges between vertices in the same partite set. So now, what is the crossing number of K223? And it turns out the crossing number of this graph is exactly 2. So again, how do you prove that it's exactly 2? You exhibit a drawing that's got 2 crossings, so you prove the upper bound, and then you prove that the lower bound, you find a lower bound for this for the crossing number, and that lower bound needs to be at least 2, and then you've got equality. So if we take C to be the crossing number of K223, we know that K223 contains K33 as a subgraph, right? That's pretty straightforward. If we go back to the drawing there, if we take those 2 vertices there and include that one there, that clearly has K33 as a subgraph, right? So we know it is not K223 is not planar, so it means that C is at least 1. So we just need to show that C is at least 2. Now, what we're going to do is consider we have to use that other theorem, so that lower bound. So consider a drawing with C crossings, and then we construct a planar graph H by replacing each crossing by a new vertex, essentially subdividing 2 crossing edges. Okay, so we are pretty much adding how many vertices? We're adding C vertices, and each time we place a vertex at a crossing, we're increasing the number of edges with 2. So in total, we've got the size of K223, which is 16 plus 2 times C, that's the size. Now H is planar, so we have that the size is at most that, and then plugging in we get a inequality. Now what we want to prove is we want to prove that strict inequality holds, because that is going to imply that C is at least 2. Right, so what happens if we have equality? So suppose equality holds. That must mean that that graph must be maximally planar, right? Because we prove that a graph is a planar graph is maximally planar if and only if its size is exactly equal to 3n minus 6. Right, now basically if we just consider one of the vertices we placed at a crossing, okay, we basically claim that these edges, right, have to exist in the original graph. And the reason is, if one of them doesn't exist, then you can go and add an edge, and you can go and add an edge without introducing a new crossing, right? By just placing the edge, placing this edge as close to V as possible, right? So you're never going to introduce any new crossing by doing that, and that's going to imply that your graph is not maximally planar. So you need those edges to exist. Okay, so that those edges are present in H, since otherwise they could be added close to V, contradicting the fact that H is maximal planar. Right, but these edges must also be, as I said, present in K223, and that is going to imply that these vertices are going to induce a K4. And you can see in K223 there's never any K4 present as an induced subgraph. So therefore we need strict inequality to hold, and this is going to force C to be at least 2. So you've proved an upper bound, you've proved a lower bound, and the upper bound just follows from producing a drawing with 2 crossings. Okay, and producing that drawing, we see that we've got 2 crossings there. And so therefore the crossing number of K223 is exactly equal to 2. Alright, so we're going to look just a little bit at crossing numbers of special classes of Cartesian products. So in this case, you can actually determine the crossing number of a Cartesian product of C3 with CT for T at least 3. You can determine that exactly. So in the textbook, what they just do is they take each C3 in the Cartesian product and they just label the vertices. So they'll label the vertex uj as the jth one of the vertices on the jth triangle. Vj is the other vertex on the jth triangle, and Wj is the other one. And then they note that the crossing number of this graph is at most t. So we can go and investigate this, and that's what we're going to do now. Right, so there I'm drawing the Cartesian product of C3 with itself, and if we look at the a number of crossings in this particular drawing, we've got a crossing there, we've got a crossing there, and we've got a crossing there. So the Cartesian product of the crossing number of this particular Cartesian product of this graph is specifically at most 3. Right, so it's pretty clear from here that there's already a pattern emerging here, that number there corresponds to that upper bound. So can we, how do we extend this upper bound to include indices larger than 3 in that particular case? Right, so let us assume what would be an upper bound for CR Cartesian with C4. Now, for us to do this, we can observe the following. So we can take another C3 and introduce it there. Now, to construct the Cartesian product, we need to basically delete that edge. We need to delete that edge and then join the subsequent vertices. So we have to also, of course, delete some edges as well, which we'll do now. So therefore, I am drawing it in that way there. Right, there I'm joining those 2 vertices there. I'm joining those 2 vertices there, and I'm joining those 2 vertices there. Okay, so essentially how many crossings have I introduced here? I've introduced 1 crossing there, 1 crossing there, and 1 crossing there. Right, now I must also, of course, join that vertex and those two vertices there. Right, so I haven't introduced any more crossings, so I just have to delete an edge, of course. So I've introduced 3 crossings, and there I am deleting 2 crossings. Okay, so again, I'm deleting 2 crossings there. So I've introduced 3 crossings, and I have deleted 2 crossings. So I've essentially added 1 crossing. So the original graph had 3 crossings. This graph has got 1 more. So therefore, the crossing number of this Cartesian product is at most 4. Right, so we're seeing a pattern emerging here. Right, okay, so here we've got, again, we go and redraw that, and we get the Cartesian product of C3 with C4. So let's say I want to find the an upper bound for the crossing number of the Cartesian product of C3 with C5. Then again, it's a similar procedure. So you can again go and introduce another C3. Right, there's a C3. What we're going to do is we are going to basically delete these edges here, and we're going to place the introduce the new C3 right in there, and we're going to join subsequent vertices. Now if we just go back, if the edges that we're deleting, how many crossings am I deleting in the process? So by deleting that edge, I'm eliminating crossing. There I'm eliminating another crossing. So my crossings, I've eliminated 2 crossings. Okay, so just keep that in mind when we introduce this one. Okay, so we're going to introduce it there. So I've got 2 fewer crossings than I originally started off with. So I'm going to join that edge there. I'm going to join that edge there. I'm going to join that edge there. I'm going to join it there. Then I'm going to, so I've introduced 1 crossing. There I'm introducing another crossing, and there I'm introducing another crossing. So I've deleted 2 crossings, and I've introduced 3 crossings. Okay, so again, this graph is going to have, it's going to have 5 crossings. Okay, so I mean, one can follow the same procedure repeatedly, and you can basically in general show that the crossing number of C3 Cartesian product with CT, where T is an integer, is always at most T. Okay, so the upper bound for that crossing number is T. So we want to eventually show, of course, that the crossing number of C3 Cartesian with CT is in fact exactly equal to T. Right, so now having established that the upper bound holds, we need to show that the lower bound for the crossing number is at least T. So they prove this by induction. So for T equals 3, the result is finished, because that is a theorem that's previously stated. Right, and now how they show the lower bound is they assume that it's true for a value k larger than 3, and then they prove that it's true for the value k plus 1. Right, in other words, the crossing number of C3 Cartesian ck plus 1 is at least k plus 1. Right, so that is how they do that. So so what you're going to do is you're going to take C3 Cartesian with ck plus 1. We're going to look at the structure of the graph, and then we're going to look at the number of crossings. Right, so the two cases they consider is as follows. So the first case is the case where no edge of any triangle in the Cartesian product is crossed. And then they're going to look at the second case where there is at least one triangle that has one of its edges crossed. Right. So let's. So what they now do is they consider a certain section of the graph. Right. So they consider this WJ. Right. So they take the jth triangle, and then they look at the triangle that comes after it, call it J plus 1. Right, and they only look at this section. Now what they claim is each one of these sections, if an edge doesn't cross any one of those edges of every triangle, right, then the only way edges can come through is from there. Okay, and what they do is they basically claim that each one of these HIs has at least two of its edges crossed. Right, it has at least two of its edges crossed. So if we can show that, then we will show that the graph has k plus 1 crossings. Now why is that the case? Right, so if we look at this like two sections as an example, so if you have a crossing there, if you have at least two crossings for each one of these sections, then essentially you can see it this way. You can count that triangle once. And how many triangles are there? There are k plus 1 triangles. So it's going to count that triangle. It's going to count that triangle. Every time you have two crossings, it's going to count the two triangles. So if you look at that section on its own there, and you look at the preceding section, okay, right. So basically, right, so we have that those two, say, it's a bit difficult now to illustrate this, but let's say they're two different sections, but they share that triangle there. Then if we have, say, two crossings there on those edges, say, for argument's sake, then that is going to count this triangle and that triangle. So that triangle I've already counted twice, so I'm going to count that triangle. So essentially what I'm going to do is I'm just going to count the number of edges of the cycle ck plus 1. So I'm going to count I'm going to count at least k plus 1 crossings. Right. Okay. So so my drawing is at least k plus 1 crossings if each if none of the triangle edges is intersected by another edge. Right, now if two in this section HJ, if two of those of two of these edges cross in that way that I've shown, right, then you've already got one crossing, and any one of the C3s that come before this on the cycle, right, it's going to have an edge that comes through there, or the edge has to come through there somewhere. So you're going to have at least two crossings. Okay. Then if you look at the preceding C3, right, it's gonna have to have an edge that it's going to have to have an edge that comes through there, and then another edge again. Another edge is going to have to come through there to get there, or obviously it can come through there, but it's just not allowed to cross any one of these edges by assumption. So therefore, in that case, you've got two crossings. Then you can also have a situation where, say, this other C3 lies inside there. It can certainly not lie there, because then one of the triangle edges is going to be crossed. So it, for argument's sake, lies, say, there. Okay, so let's say, for argument's sake, that C3 lies there. Then if you look at it, right, let's say for argument's sake that C3 lies there. Then if you look at all the other C3s, with the exception of the two ones that are part of HJ, they all lie on, you can form this cycle, right? The cycle is indicated in red. And these edges on this cycle is going to definitely cross that edge, and it's eventually going to come back there. Right, so again, it's going to cross. It's going to cross the edges of the section HJ at least twice. There's no other way. Right, so if each one of these sections, the section HJ, if it has two crossings, you can then apply the argument to every HJ for all J's, right? So again, those number of crossings, you can actually match it to the actual number of vertices on the cycle CT, which is T, right? So you're going to have at least T crossings. Right, so the other case we need to go and look at is there is at least one triangle that has an edge that is crossed. All right, so there you've got the triangle with one of its edges crossed. Okay, so remember what we want to show. We want to show that the lower bound for the crossing number of C3 Cartesian CK plus 1 is at least K plus 1. So we're going to assume by contradiction that it isn't. Let's say it's strictly less than K plus 1. So you're going to form a new graph now, which you're going to form by deleting these edges here. Okay, you're going to delete these edges, and so how many crossings have I eliminated? I've eliminated one crossing. But what is this new graph that I get? This new graph is going to be a subdivision of C3 Cartesian with CK. It's going to be a subdivision. These are going to represent these vertices here. If I delete them and I pretty much just extend these edges, right, and whatever vertices I have there, if I go and join them there, I'm going to get C3 CK. And that is essentially what I'm doing there is I'm getting a subdivision. So how many crossings does C3CK have? We said it's got at most how many crossings? We have now, how many crossings does this graph have? By assumption, at most K crossings. And by deleting the edges of that triangle, we've eliminated another crossing. Right, so essentially it's going to imply that the crossing number, because with a subdivision you don't introduce any new crossings, and that is going to imply that the crossing number of C3 CK is going to be at most K minus 1, which is a contradiction.